The topic for today is basics of feature engineering. If you've been in the field for quite some time, you would know most of these. So again, if you feel this is too basic for you, please feel free to drop out. I won't hold that against you. But this is if somebody is just getting started and wants to know all the different kinds of things they can do while trying to engineer features in tabular data sets, then this will be a useful session for you. Okay, I usually have an about me slide, but I think I've already introduced myself. So quickly on the agenda for today, like I said, if this is something that you already know, then it will be a sort of a repetition for you. Otherwise, it will be something very interesting. So we will look at what is feature engineering, what's the kind of data source you have, different kinds of variables, numeric data, and the techniques that you can use on your features that involve numeric data. You have categorical data and the techniques that you can use to to perform feature engineering on your categorical data. I have one small feature engineering tip which I found useful, which I will share towards the end. And then finally, we have some time for question and answers. It looks a lot, but it isn't a lot because I will uh, perhaps. I mean, it looks a lot, but I hope I will be able to convey it in a way that it goes into your head and you don't have to think too much. Now, first question: what is feature engineering, right? So, uh, in the context of building machine learning models and machine learning systems, feature engineering is often not the least talked about, but it is not very well described, or not a lot of papers are written on this. But it's an extremely important and crucial part of your pipeline. So if you take a look at the entire machine learning modeling system, uh, you see that the feature engineering part precedes the modeling part, and it is a crucial part in the pipeline. It's something that is your input to your modeling, and you have different sources of data. You have source one, source two. You can have all kinds of data sets that exist, uh, and you store them as raw data. So that's where your data engineers come in. They collect data from different sources and store them in your data warehouses, in your databases, and then you have this raw data being converted into features that could be fed into your machine learning models. And then your machine learning models could provide insights, could provide predictions, could provide forecasts, etc., based on what you want to do. So the important part of translating your raw data to something that you can feed to your models is called feature engineering. Right now, this is I think a figure I took from a book. I but it's highlighting the clean and transform part, but it's not just clean and transform that you do. So that's what I was trying to say. It's not just clean and transform that you do. It's even more than that. I mean, it depends on your definition of data cleaning, right? So if you say feature engineering is essentially data cleaning, then yes. But to me, it's not just data cleaning, but it's understanding the data with respect to the task you have at hand and with respect to your end objective, right? So what kind of modeling algorithm you want to use, what kind of business problem you're trying to solve, and what kind of data you have available. So combination all of this is what influences your feature engineering. So this is where feature engineering sits in the context of your entire machine learning system. I have a small example here of, I mean, I will go into details of each of these techniques, but again, so how does this entire process work, right? So you have a real world activity. Maybe you're trying to predict, which is again a slippery slope because you don't want to do this. You're trying to predict, say, corona. Uh, Presence of COVID in a patient. You collect data on the patient gender, the oxygen level or pulse rate, etc. Uh, and if you see the way the raw data is collected is like patient gender, you just say male or female, right? So you don't really you don't really think of writing it in a form that is useful for your modeling. You are writing it in human readable form, which brings me to another definition of feature engineering, right? Transformation of data that is human engineered to machine engineered, right? So you could think of it in that way as well. So you have data on different attributes and you store them the way you collect the data. you just dump it there, and then you do this feature engineering where you convert, say, male and female into 1 and 0, right? So where male stands for 1, female stands for 0, and then use this converted data set, which is the feature engineered data set with features, into your machine learning system. This is a plain simple example of it. Of course, feature engineering is a lot more involved than what you see here, but this is good to get started, right? So this is how the distillation process happens, and after this step is your modeling and your predictions, right? So this is how your entire pipeline works. Moving on to basics of feature engineering, the topic for which all of you are here today. So now that we've understood what is feature engineering, let's start looking into each of these one by one. Now, in general, as a data scientist or a machine learning engineer, you work with lots of different data sources. And this is why I specifically said uh, basics of feature engineering featuring tabular data, right? So, because the kind of data sources you have may vary from, say, image of a cat or a dog or any other object that you want to classify, recognize, etc. It may vary from it may be in the form of text as a book or a blog or a comment or a tweet or any other form of text. It may be in the form of sound. It may be somebody's speech, somebody's song, somebody playing an instrument or anything else, or it may be in the form of a matrix. There are x number of rows, m number of rows, and n number of columns. So basically, 4 different kinds of data sources here: image, text, audio, and tabular. And we are going to focus on tabular for today. This is important to clarify because there are different feature engineering techniques for image, for audio, for text, and for tabular, right? So, and eventually, if you think about it, all of your image, your audio, your text are converted to tabular in the form of matrix, but the processes that you go through are different for each. But in our case specifically, we look at data that was originally stored as rows and columns, like the one I showed you in the earlier example of about COVID patients, right? So you are going and collecting data in the form of rows and columns. So this is our data set. This is the kind of data source we'll be looking into today, and the different kinds of techniques that you can use to to engineer features from this. I'm not going to look at questions right now. I don't know if you're even dropping in questions, but if you have any questions, please feel free to drop in the questions or comment section, and then I can take a look towards the end of the session. Now, different kinds of variables. Right now, we are starting to look into tabular data set, and when we start seeing tabular data, we see something very interesting. We see there are different kinds of data that are being stored, right? So there is numerical data in some columns. There is categorical data in some columns. And what do I mean by numerical data, right? So numerical data is essentially data that is made of numbers, right? So you have age, weight, number of children, shoe size, height of people. All these are basically numbers that are stored. And then you have categories, right? Categories of, say, eye color, your gender, your blood type, ethnicity, the kind of grades that you're getting. So all these are different categories. So these are two like high level kinds of data that you see, but and there are further subdivisions within each of these data sets. So if you see, numerical data is of continuous type or of discrete type. So what is continuous type data? So it's a real valued number. You have age, weight, blood pressure, all of these all of these numbers are continuous in that they can vary continuously from 1 to, I mean, in theory, infinity, but it's all numbers on a real number line. Discrete are those numbers that would probably be integers, right? So it could be like, for example, shoe size can be maybe 2 or 3 or 4 or 5, but it couldn't perhaps be 2.1 or 2.2, right? So shoe sizes are discrete, so you jump one number to another. Or number of children, you can't have 2.5 children. You would either have 2 children or no children or one children or one child, etc. So Even in the even in numerical data, you have different kinds. You have continuous and discrete. Continuous is numbers that continuously increase or decrease. Discrete is numbers that increase or decrease in steps. And sorry, categorical data is either ordinal or nominal. And this is a slight difference. There's a slight difference between these two. So ordinal data in this case has a hierarchy. So pain severity, it either increases in order or decreases in order, right? So if you had high pain, then you have little lesser pain and lesser pain and lesser pain and then no pain. Satisfaction ratings or mood. So you ask people about how their experience was doing something, and then they say very satisfied, satisfied, less satisfied, not at all satisfied. So there is an order in which these responses are being collected. There's an order to which different people will rate. And yet these are different categories, right? So very satisfied is one category, satisfied is another category, not satisfied another. So people will rate different categorical answers, but these categories themselves have an order. Very satisfied means something more than, say, just satisfied. And satisfied is more positive than, say, not satisfied. And again, not satisfied is much more positive than very, very not satisfied or dissatisfied, largely dissatisfied. So there's an order to which people respond in categories, and that's why it's called ordinal categorical data. Okay, I hope this is clear. And then you have nominal categorical data, which is essentially like if you have colors, right? You have red, blue, green, yellow, whatever color that you have. There's no particular order, but these are different categories of things. Like, again, dog breed, blood type. So you have A positive, O positive blood. So all these are different categories of blood, but there's nothing like O positive blood is, say, superior than A positive blood, right? So these are different categories of blood. Yeah, there are different properties of each of them, and that's why they are different categories, because they vary and they have their own properties, but there is no order when you try and compare them. And that's why this is nominal categorical data. So summarizing, you have data, numerical, categorical. Numerical is continuous or discrete. Categorical is ordinal or nominal. And this is basically all the kind of data that you will see in tabular data sets, right? It's either one or the other form of this. And we are going to use this data and keep manipulating based on the kind of data it is and based on the requirements that we have. All right, so with this, I move on to the next slide, which is numeric data. Now, I think there are different ways of approaching this, but one way of approaching this is asking questions of your data. So you ask questions on magnitude. So does the magnitude of your data matter, right? So if my data is increasing by a lot of magnitude or decreasing by a lot of magnitude, does that even matter to what I'm trying to do, to what I'm trying to model? So before I proceed further, so just want to clarify that feature engineering doesn't work in isolation, doesn't work in vacuum. Like I said earlier as well, uh, feature engineering is combination of the data set you have and the model that you're trying to build, the model that you're trying to use, and the purpose that the model has to serve, right? So all of these three things put together influence your feature engineering. And when it is numeric data, you think and you ask yourself, does it matter? Is the sign on the numeric data column indicative? If you have a plus sign or a minus sign in your numeric data, does that mean something? Does that, like, for example, there are scenarios, I doesn't apply to numeric data, but I just wanted to share now, where you assign a -1 to a value that does not belong to your expected distribution or to your expected values. It would be in categoric data, but I'm just saying it now because it just came up. So in that case, sign is indicative. Sign is indicative of this being a value that is not supposed to be part of the expected distribution. right? So this is something that I have done, and other people in the industry do, is we assign a default value, which could be -1, which could be not zero if your zero is part of your expected values, or -999. So you use these kind of values to indicate that this is an out of distribution value, or an unexpected value. In this case, sign is indicative, right? So because you're expecting positive values, you write negative value and something. So in that case, perhaps that is also a way to tell the modeler that, hey, this is something you might want to ignore, or maybe something you want to consider as an outlier. So sign is indicative in that case. It might not apply to numeric data, but in general, for feature engineering, sign becomes very indicative. Level of granularity. So what is the level of granularity that of the data that you have, and can you go further in the level of granularity that you have? Can you combine these different columns to, again, maybe get a column that represents all of the sub columns? So and how does that influence with the magnitude, right? So by doing that, does your magnitude increase a lot, or does it remain unaffected? So all these are questions that you would want to ask when you look at a numeric column in your data set when you're feature engineering. And like I said, the does it matter question, the sign indicative question, comes from the data that you have, the data generating process. Like I said, the data generating process in my example influenced the decisions, influenced my understanding of the data. It comes from the model that you're using. It comes from the task you want to achieve. Scale, and this is one of the common themes that you will see going forward as well. Scale becomes very important. You try to figure out what are the min and maximum values, and is the model that you're going to use scale dependent, right? Some models are dependent on scale, some models are not dependent on scale. We will see that in the next few slides. So if your model is scale dependent, then you would want to say normalize your data, and we will see what normalization means. And if your model is not scale dependent, then good for you, you can use that model. But if your input is growing over a period of time, and what I mean in that case is, for example, you're using counts of something as an example, and uh, that is only going to keep increasing, for example, right? Um, let's say counts of user on your platform, just a random example, counts of users on your platform. There are a lot of users already on your platform, and you're increasing count every day, trying to increase count every day. That's why your growth team exists. And if that is your feature, every day you will keep, and assuming it's a positively growing company, and you are getting new users every day, your count will keep increasing every day. It's not going to stop, right? Or let's a more simpler example, right? Count of songs that are created in the world, in an area, for example. There will be more and more songs that are going to be created by people every day. So that is a continuously growing input over a period of time. In this case, you might again run into problems while trying to feature engineer. So in this case, you might want to rescale. Distribution of your numeric data, and basically questions like, does your model have assumptions about your features? And the most popular question here, or example here, is that linear regression assumes Gaussian distribution of your residuals, of your prediction errors. And in that case, are you making sure that your numeric data, your data distribution, is in line with your model assumption, right? So these are questions that you ask of your data set. You look at the data set, and then you ask these questions. Which again wanted to remind you guys also, if you have questions while you look at my presentation, please drop them in the questions or in the chat section. I will not be able to take a look now, but I can take a look at the end. But if you have any questions that come to your mind while I talk, please feel free to drop them. Okay, so this is what I wanted to discuss about numeric data and the questions you want to ask while you take a look at such a data set. There could be more questions. I'm not saying this is all the data questions that you would want to ask, but this is a good start, I would say. You look at the data, you ask these questions, you see what what answers you get from the data, and then use that to define your further course of action. Now let's move on to the first technique, feature engineering technique for today. It's called binarization, and I will introduce this to you with an example. The example is this: so you have a system that you want to build, and let's say you want to build a recommendation system. And the task that you have at hand is you want to be able to represent user preference, right? So you want to build a recommendation system, and the task you have at hand is you want to represent user preference. And user preference could be like, again, let's say uh, how many songs listens. Okay, so yeah, the so the recommendation system is you want to recommend let's say songs, and you have user preference, which is essentially the counts of the number of songs that a person listens to. Now what would happen in this case is something that I want you guys to think a little bit. You just have the counts, right? You have the raw counts. I listen to a song 10 times, you listen to that song 20 times, somebody else listens to that song 1000 times. You want to be able to represent user preference. You don't want to do anything else. You just want to showcase that this guy is interested in this. And in such cases, the problem there is that you will have a skew in data distribution. You will run into issues while trying to represent the interest, because you the data that is more often repeated will likely get the larger uh, so what will happen is the song that has the most number of counts or the most number of listens would be interpreted as the most favorite one, even though that might be the favorite of only a subset of people, right? It might not equally divide the user preference amongst the entire set of songs that you have. So that is the problem you face when you have raw counts and raw counts are unequally represented. So one way of solving this is binarization. And what you do in this is you convert this raw count real number into a binary number. Uh, and as shown in this example, you have a row called count, a column called count with different counts of, say, this listens to of a song, and then you binarize the data. Basically, wherever there is an intent or wherever there is an interest, you give that a label 1, and wherever there is no listen, you give that a label 0. And now all songs that are often listened to or less listened to are equivalent, right? So now they become now what is happening is wherever there is a listen, that is an expression of interest, and that is being recorded as a 1. And wherever there is no listen, for some songs they might be not a listen by a user, so you would say this is perhaps not of interest to the user, and that is being assigned a 0. And that is the process of binarization. So converting your numeric column with varying counts to a binary column. Often binarization is done not often it's done, but I mean it depends on the kind of problem you want to solve. But if you do it, you do it for a target column, right? So it's again, when you're trying to build a machine learning system, you have your feature set and you have your target column in the context of a supervised machine learning problem. And so in this case, like I said, your task is to represent user preference. So that is your target column, and your target column is your counts. So what you're technically doing here is not feature engineering, but target engineering. And target engineering itself is a different field of its own. I'm not going to get into the depths of target engineering today. Maybe that's for another time. But what you are doing here is, in a way, target engineering, where you're changing the task at hand because you're adopting the counts to a binary value. And that is binarization. Moving on to quantization or binning, and this is something that we have been doing for quite a while. We've done this in school, we've done in many different places. We've used different names for this, right? And this is very simple, but I will also show this to you in the form of an example, right? And now again, you want to build a recommendation system, and your task is collaborative filtering. Rather than just representing user preference, you want to say that I want to recommend something based on the other person's interest. And now the issue is different people have different interests, and again there's a large variation of value, right? So the minimum and the maximum values are varying by a lot of different uh, but there's a large variance. And one way to solve this again is to convert your continuous number into a discrete number and then use that as your feature. So what you do here is you have your counts again, 20, 0, 0, 100. You convert that to a bin, and then you reduce the number of values that you want to look at while you're doing your feature engineering. So 20 goes in a bin of 20 to 30. And now again, you either keep it as a bin or you assign that bin a label and use that label as your feature. And in this case, for example, if your values range between 0 to 100, you've already reduced that range to 0 to 5 by quantization or binning. You create bins and then use those bins, you give those bins an assigned label and use that label as a feature. So you've already reduced the range of your values to be restricted between the defined categories, or to define not category but the range of values. It's not technically a category but a range of values. So, and this is useful for you to minimize smaller variations, right? If there are smaller variations, uh, it's still considered belonging to the same group. Larger variations would be again dealt with because you are now transforming so the column had lots of different values and it was varying from say 0 to 100, so it had a lot of uh, it was in a larger space and that is being transformed to a smaller space of values, smaller set of values. So you lose out on the smaller differences when you do this, but you retain the essence of uh, being in that same dimension, right? So that is retained why when you do quantization or binning. Okay, and I will move on to feature scaling or normalization. And this is a continuation of the previous idea where you want to scale your features when they go out of hand, when there are different kinds of features that have like a lot of ranges in values. So you would want to do this to contain them. And the reason you want to do this is because there are different kinds of models. You have linear model, logistic model, you have tree-based model. All of these models have their own way of performing of forming the decision boundaries, and they're affected therefore differently by the scale of the feature, right? Changing the scale of the feature is called feature scaling or feature normalization. Moving on to, yeah, feature scaling is useful in situations where different input features vary wildly in scale. So yeah, back to the point that I was trying to make. Yeah, I just remembered. So different kinds of model, linear, logistic, tree-based, etc., are affected differently by the scale of feature, and some of these models are even scale invariant. So, for example, tree-based models are models that do not depend on scale because of the way they form their decision boundaries. They don't care about the variations in your minimum and maximum values or what is the kind of distribution. I mean, that is of course useful for them to find those uh, the points at which they form the trees, but that is not influencing the way they form the decision boundary, right? I mean, it influences the way they form the decision boundary, but that is not an impediment because they are not affected by changes in scales of different feature values. So we will look at a few techniques. The first one that we will look at is called min-max scaling or normalization. And what happens in this case is you have again a numerical column, and this numerical column will be rescaled to have bounded values between 0 and 1. And that's why it's called min-max scaling, where with a value of with a min value of 0 and a max value of 1. And due to the bounded range, and this is what I was trying to say, due to the bounded range, we will have smaller standard deviations, suppressing the effect of outliers. And the way it happens is that you have an input feature with different values in input, and then you perform normalization, in this case min-max scaling, and you get a normalized feature which has values that are between 0 and 1. And the formula to do that is also mentioned in the diagram there. You can just take a look. X bar is equal to x minus min of x divided by max of x minus min of x, right? And all your normalized features, all the values in your normalized feature column will be between 0 and 1. And this restricts the scale of the feature to be between 0 and 1. And this is a useful property for some of the modeling techniques that we have. Some modeling techniques, of course, are not affected, like I mentioned earlier, but some modeling techniques want you to restrict the range for, or rather, want you to have similar ranges for all of your features or most of your features, right? But because you're bounding your input and output, you will have smaller standard deviation, and the effect of outliers would be minimized. Because everything, like again, if you had an outlier, right, even that, if you want to visualize, if you had a big outlier, even that would be rescaled to a value between 0 and 1, right? So that is what you will lose when you're trying to do min-max scaling. But the advantage there is that you do this and have different features that have comparable scales. Okay, I hope this gives you an idea of min-max scaling. You can also go to, say, scikit-learn. They have a min-max scaler. You can give your input, and then it will automatically give you this normalized feature. Moving on to next feature scaling technique called as standardization. And in this case, what happens is that the rescaled feature will have mu equal to 0 and sigma equal to 1. So your feature might have a different mean and different standard deviation because of the data generating process that generated that data. But when you apply standardization on that, you would shift the mean of your distribution to 0 and have a standard deviation of 1. And standardization may be useful in the case of distance and gradient descent based algorithms. And this is, again, going back to your linear regression and other algorithms that rely on distance. And if you have a lot of different columns with different scales or different ranges, your distances are affected, and as a result, you are perhaps dealing with sparse matrices, sparse dimensions, and that could be problematic, right, when you're trying to model. So standardization will help you will help you tackle that. So the example here is the similar one that we saw earlier. So you have input column with 0, 1, 2, 3, 4, 5 as your inputs, and then you perform standardization, and your standardized input is a different value, but it is, if you see this closely, it is not restricted between, say, 0 and 1 or a minimum and a maximum value, but it is shifted. The distribution that was originally seen is now shifted to have a mean of 0 and a standard deviation of 1. And the formula is x bar is equal to x minus mu divided by your standard deviation, right? The advantage again here is you have your standardized input in a range that is comparable across your different features, and that is something that your distance and gradient descent based algorithms would prefer. Okay. Also, one quick tip on this, which I found while reading about this, is that uh, one of the authors or one of the professors called Sebastian Rashka. He has a book called Python Machine Learning, and I was reading through his material, and he says, as a rule of thumb, when to use standardization. So the question he was trying to answer is when to use standardization versus min-max scaling, which one to prefer. So he says there is no particular way of saying this is the better one. Use this. It's also task, like I said, task dependent and the data set you have. But as a rule of thumb, he suggested to apply standardization first and then maybe try normalization. Because again, also the assumption there is you're trying to use a linear model to model your data set. So then you could perhaps try standardization first and then take a look at normalization. Okay, now we've completed numerical data set. Let's move on to categorical data. And this is a very interesting type of data set. I will talk about categorical data a little bit now. So what matters more? How different versus just different? And this is how you define categorical data. If it is how different, then that data is numerical. But if it is just different, then that data is categorical. To give you an example to visualize this, so when you're trying to visualize different categories, like I said, different colors, right? You have red, blue, yellow, green. You're not visualizing those differences in terms of numbers, but you are thinking of those differences as different properties of an object, right? So red colored something is different from green colored something because of the way it appears, but not, it's not how different, but that it's different because it is just different. It has different properties. It looks different, or it has different features. So that is how you would say this defines numerical and categorical uh, differently, right? So how different versus just different. But in categorical, we have, like I said earlier, ordinal and nominal, and we will start looking into what each of them are. And like I gave the example earlier, so ordinal has uh, like order in the categories, and nominal is independent of order in the categories. In this case, I have, for the ordinal example, I have your reviews for the session, for this session perhaps. If you're extremely satisfied, satisfied, or not satisfied, so there is an order to what I am talking about. And in the case of nominal, it could be cities, right? There's no order when I'm describing cities. Of course, I'm not trying to say which city is better. I'm not trying to answer that question. I'm just saying cities, and there's no order there. So moving on to the first feature engineering technique, which is called label encoding. It's a very simple technique, as you will find out. Each label is converted to an integer value, and it's as simple as that, right? A mapping is created for every label in the feature to its equivalent numeric representation. I will show you an example, and then it will be crystal clear, right? So you have an input feature, and then you label encoded, and you have a label encoded feature. Your input feature is extremely satisfied, satisfied, or not satisfied. Like we are trying to use ordinal data, categorical data, and trying to convert that into its numerical representation. So if this is how you store your input, you say, if it is not satisfied, I will assign it a 0. If it is satisfied, I will assign it a 1. If it is extremely satisfied, I will assign it a 2. And this is basically encoding the labels. Each of the categories, you give an encoded number, and your label encoding feature is ready. Right? And this is something you can go ahead and use further in your machine learning models. Conversion of your string or text-based input into a numeric input. Label encoding, very simple. Just assign, and of course you will want to store this as a dictionary somewhere, as a key value mapping, where you assign your input as your key and your encoded input as your value. Okay, you want to store this mapping because this is going to be useful for you to check back later. So that is what you do in label encoding. Assign a dictionary and then use that to replace your keys with your values. One hot encoding, this is a very interesting technique. And in this, and like I showed you the previous example, it was for an ordinal data source, ordinal categorical data source. In this case, we will see for the ones that don't have an order, the normal one. So features do not have any order. Each level of the categorical feature will get a new column. And this is how one hot encoding basically works. And each category is mapped 0 or 1 depending on the index of the category. And this is, I will show you to you again with an example. We saw the example of Bangalore, Bangkok, Bangalore, and Berlin as different cities. And now the one hot encoded feature is on the right side of your input, which is basically for Bangkok. Uh, so Bangkok is present on row 0. Berlin is present, sorry, Bangkok is on row 0, Bangalore is on row 1, and Berlin is on row 2. So whichever, so row 0 is the index. So 0 is the index. Row of 1, Bangalore, for Bangalore, 1 is the index, and for Berlin, 2 is the index. So we will convert that to a value of 1 wherever the index appears, right? So for Bangkok, I will create a new column. For Bangalore, I will create a new column. For Berlin, I will go and create a new column. For Bangkok, it was originally at row 0, and therefore in my new column, that part will be 1. Bangalore was originally at row 1, and therefore in my new column, whenever row is equal to 1, I will assign a 1. That's the way one hot encoding works. So all the different categories that you have in your input, you take those and create a column for each of them, right? You have different categories, create a column for each of them, and wherever they appear in the original data set, take the index of that and assign that a 1. And that is how one hot encoding works. It's very simple. You have different categories, take the categories, create a column for each of them. Wherever how do you assign ones? You assign ones based on where it was there in the original feature before you encode it. So whichever row index of that row, just take that and assign that as 1. And that is one hot encoding for you. And this is an again important technique for for converting your categorical data into numerical data that your models can use. Now there are few variations here. I have not included them, but I will mention them. There's dummy encoding and effect coding rather, that run variations of this technique. I would suggest, if you're really interested, suggest you to search for these terms and read more on them. But I just wanted to explain the concept of one hot encoding. How much time do I have? I have another 10 to 13 minutes. I think, yeah, we have enough time for question and answers then. This feature hashing is an interesting technique. I have not used this personally. The next two techniques I have not used personally, but I have used all the previous techniques personally. Like all of what I have shown you so far, I have tried to do them personally. But this is something that I found while reading, and it was very interesting for me. So I've kept this. There's also another one following this, which we will look at, bin counting. But what is feature hashing? So feature hashing is another technique to convert categorical data into a numerical, into a data set that can be used by the model. And this is useful while dealing with large categorical variables. And one of the problems of one hot encoding is that, right? So if when your dimensions, when the number of categories you have in your data set increases exponentially, or when you have a large number of categories, then you increase the number of columns that you have in your data set, and that leads to a lot of different dimensions, and then they have a lot of different problems. You have curves of dimensionality, you have compute problems, and that is problematic, right? So how can we find ways to reduce the dimensions that we have and yet represent all categories? And that's why there are different people trying out different techniques, and one of them is feature hashing. So useful while dealing with large categorical variables, restricts the final dimensions, and therefore can be time and space efficient. That's what I was telling, right? So that the problem with one hot encoding is that you can have a lot of different dimensions, and what you're trying to do here is restrict that. One drawback is that collisions may occur. Uh, I don't have time to explain collisions here now, but I will just say it in simple words is that if you have if you understand key value pairs, if you have two different keys and if they are both assigned the same value, then that's a collision, right? And then you don't know which key will which value should the key, should be given to which key. So the drawback with feature hashing is that this might occur. But of course, there are also ways to tackle this, and this is also something that doesn't happen as often as you expect. So that's why some people expect to live with it. Now, let me show feature hashing with an example, and hope that will explain what feature hashing is. So you have your input feature, you do feature hashing, you have your hashed feature. What happens? How do you do this feature hashing? It's a very interesting way of doing. Like I said, I've not personally done this, but it's super interesting. So you have your input, Bangkok, Bangalore, Berlin. We've been seeing this example. I will take one row and show you what happens, right? So if you have Bangkok, you go ahead and hash that. Now, I expect you to know what hashing is in computer science, but if you don't know, it's fine. Let's just assume that when you hash something, it assigns you a unique number. Yeah, let's just say that. So hashing of hash function, when you pass Bangkok through a hash function, it will give you this 111, for example. Okay, it's not 111. Depends on the kind of hash function you use, but let's say in this hash function gives you 111. So you will take that hash functions 111, and then you will uh, go and divide that to a number 100 or something that you decide based on the scale that you want, and then take the remainder. So that's what you're doing in the next step. So you have Bangkok, you've hashed that, you've got 111. You take that value and you run a modulo operation, which will give you the remainder, and use that as your feature index. So I is equal to 11 is what you find out from this. So 111 divided by 100, the remainder is 11. You take that and then go ahead and actually on the rightmost table, it should be x underscore 11. So I think that one is hidden inside that margin, but what x, so there's x0, so on, x11, so on, x32. So you will go ahead and for x11 you assign a 1. That is where Bangkok occurs, and the rest are basically zeros or null values, right? So this is the idea of feature hashing. And then how many uh, how many different columns that you should have eventually or finally is divided by the modulo operation that you run. So in this case, modulo 100 will give you a certain number of columns. If you increase or decrease the modulo value, your number of columns will change accordingly as well. The number of columns that you use to represent your data will change accordingly as well. Again, this is not an accurate, there's no like actual hash function, or there's no actual modulo divisions happening here. This is a toy example, but this is how feature hashing happens. And it's a very interesting technique where you can reduce the number of final columns based on the hash value, the modulo operation, and then and yet you're still able to represent your categorical data that could be used for your modeling purpose. And that is feature hashing. I have another 5 minutes and I will quickly take you through bin counting. I'm not going to explain this concept to you here today because it is slightly more complicated, but I will tell you what it is. So it is useful again with dealing with large categorical variables. It has been used in applications such as ad click-through rate prediction, hardware branch prediction, etc. And rather than so this is the concept, right, for bin counting. Rather than using just the value of categorical column as feature, you instead use the conditional probability of the target under that value. Now there is an example for this as well that I found out while reading. You will also find it. I can share links with you later, but I didn't have the time to put that in here, and also it takes some time to explain that. So it's a bit more complicated to explain. So I'm just going to say that there's another technique called bin counting, and rather than using just the value of categorical column, you use the categorical column and the target value, and then you calculate a conditional probability based on these two things. So it, and therefore it converts a categorical variable into a statistic about the value, right? It's not like a direct conversion of the categorical value, but there is a calculated column, calculated value based on your categorical column and your target data. And that is what bin counting does. Okay. So lastly, this is the last slide that I have for you today, and I think I'm just on time as I will be wrapping up after this. So one feature engineering tip is not use your brains. I was about to say that, but okay, of course, use your brains. But what's more important is to have that domain knowledge, right? So if you have the domain knowledge and the task at hand clearly defined, then your feature engineering becomes way more easier, right? So use your brain, use your domain knowledge, use the data you have at hand, and engineer features to the task you have at hand. Because different tasks require you to think of features differently. Some of them might require counts, some of them might require binarization, some of them might require feature scaling. So again, all these techniques that I mentioned earlier are again useful uh, if you have a task at hand, if you have the data set, so you can use that to model the problem statement based on the context of your domain knowledge and what you're trying to solve. But that is not all. Use all of your raw data, use all of your domain knowledge. And one quick tip, and this is where the tip part comes in, is to use statistics. And when I say statistics, I don't mean complicated statistics. I just mean basic statistics. Your distributions and your percentiles or your mean, median, mode. So what you do is and this is something that I learned from, I think, Abhishek Thakur's online Kaggle notebook, and where he has different features, different columns, and for each of them, he goes ahead and calculates mean, median, mode, standard deviation, variance, and all these different statistical values for that column, right? So, and because the reasoning behind that is you might capture a pattern that doesn't exist in the raw counts, but might be in the mean of that distribution. You might capture a pattern that might be present in the standard deviations rather than in the, say, scaled feature, right? So apart from all the different techniques that I mentioned earlier today, this is another tip that I learned from reading Kaggle notebooks, and also something that I've seen work in practice somewhat, right? So sometimes I've seen median values of some feature have more predictive power than just that feature itself. Ultimately, your aim is to increase the predictive power of your features, and this is one way of trying to do that. And that's all I have for you today. Thank you so much for listening.